I'm sharing my screen. Okay, good afternoon. Okay, so we are continuing today the session that we started yesterday, okay, which is the yield line analysis of slabs. And I think we covered the introduction, and I think we reached the point where we did the assumptions here, okay? I think we reached up to this point where we looked at the assumptions of the yield line theory of slabs, and we covered the assumptions. So now the next thing I'm going to do now is actually looking at a proper slab with some yield lines, okay? And these are some examples of how the cracks or the yield lines develop in some of the examples of slabs, okay? The first example, this one here, top left, is a square slab which is simply supported on 4 edges. So we have a square slab and it's supported on 4 edges. Excuse me. And this is how the yield lines will look like. So you have like a cross going across the diagonals because it's square. So we have symmetry in all directions. The example on the right, top right, we have a rectangular slab which is supported on 2 edges only, and the other 2 edges are free. So it's free on 2 edges and supported, simply supported on 2 edges. So we have one single line going across, which is in the middle here, this is where we have the maximum curvature, and therefore the yield line will run across the middle of the slab as shown here. I mean the same here for the square slab. The maximum curvature is in the center here. So this is where the yield lines will start, and then they propagate and spread to the intersection of the axis of rotations, the edges here, okay? The next example, which is at the bottom left corner here, we have this time a slab which is rectangular, but this time it's fixed on the edges. It's not simply supported, but fixed. So it's fully fixed on the edges here. So therefore, in addition to the positive yield lines here that we shown in black color, these are the positive yield lines. We also have negative yield lines shown in red here. What are the negative yield lines to do with what? Why do we have negative yield lines?
Opposite direction of curvature.
Yeah, but why? What do we? If you have a say, if you take a strip, what do we have at the edges? Yeah, but if it's fixed, what do you have at the? If you have a support which is fixed, what do you have there at the support? You have a moment which is negative. You have a hogging moment. You have a negative moment, isn't it? Yeah, like a cantilever. If you have a cantilever, at the end you have a negative moment at the support. It's exactly the same here. We have positive moments in the middle, but we have negative moments at the fixed support, and therefore we have negative yield lines. So in addition to the positive yield lines, we also have negative yield lines. Say it's the same story here. We have got a slab which is rectangular, but it's fixed on 2 edges. So in addition to the positive yield lines that you have here, where the curvature is maximum, you also have negative yield lines. You have negative yield lines because the supports are fixed. Clear? Okay. So let's look at next. Next, I've got another 4 examples. This example here, top left corner, we have a trapezoidal shape. Now the trapezoid shape is no different from a rectangular shape. It's just trapezoidal. So you have exactly the same kind of yield lines, okay? It's simple supported, so you've got these yield lines for a trapezoidal shape. Now, when this case here, we have a rectangular slab, but supported on 3 edges only, simply supported on 3 edges. That, depending on the ratio of this length to this length, you either have the mechanism in black here in the dark color, or you have the one in red. But that all depends on the ratio, the relative ratios of this length to this length, okay? In most of the cases, you have the one in black here color, but it's possible to have this one here, depending on the ratio. We will look at examples in the future, just to show you how it works, okay? So you've got that or that. I mean, the next one is a slab that has got 5 sides, right? But it's only supported on 4 of the sides, and it's free on this side here. Now, how do you decide on the yield line? Basically, the yield line will start where the curvature is maximum. So it's going to start somewhere here. This is where the maximum curvature is. Then it's going to propagate to the intersection of the lines of rotations. For example, this edge and this edge are supported. So the slab is going to rotate about these 2 about these 2 sides. So therefore, the yield line will go there. And then these 2 edges here, the slab will rotate about this edge and this edge. So the yield line will go there, okay? And then we have a yield line here between this edge and this edge. And finally, if you extend this side here, if you extend this side and you extend this side here, they will intersect at some point. And then the yield line will go from there towards that virtual point, okay? So you end up with this yield line here. Is that clear? Okay. Finally, this is an example where we have got a slab which is supported on 2 edges, but on the other side, it's supported on 2 columns. So we have 2 columns. I remember what we said earlier, yesterday. We said that the yield lines will go over the yield lines. Yeah, over the columns. Yeah, do you remember that? That was one of the things we said yesterday. So basically, so what you do then, you take the axis of rotation about the columns, extend it. You take the axis of rotation of this side, extend it, and you take the axis of rotation, which is this side here, extend it, and then it gives you the points here of intersection, and the yield will start with the maximum curvature, and then you join to the points of intersection of the points of rotation, axis of rotation. Is that clear? So it's very easy to do. You just have to follow, the rules, which is that the yield line starts at the maximum points of curvature and then extends to the intersection where the axis of rotations are. Clear? Yeah. I mean, these are really what I've given you here are the most common ones that we are going to encounter, and depending on how much time we have, I will be looking at an example of each one, just to show you how we analyze slabs with different boundary conditions. Okay. Any questions? Is that clear? Okay. Now I would like to talk now about moments and rotation vectors. Okay, sign convention. Now, why do we need to talk about sign convention? The reason we need to talk about the sign convention for moments and rotations is because, unlike beams and frames, where we are dealing with unidimensional structures, a slab is really 2D. So you've got dimensions in two directions. Yeah, it's not like a frame, because everything that we did in the past, we have the frame, so you're working in one dimension only. Okay, with the slabs, really you're working in two dimensions. All right, you're working in two dimensions, and therefore, when you have got two dimensions, x and y directions, therefore, when you project on the x-axis and the y-axis, you need some convention. So we are going to define the moment in terms of a vector, and we define the rotation in terms of a vector, because then when I have vectors, I can project the vectors onto the axis that I want. Is that clear? So how do we convert the moment and the rotation into vectors? This is what I'm going to explain here. Okay, just focus with me on this slab here. Look at this slab. Okay, we have a slab here, rectangular slab, which is simply supported on two edges, on these two edges here. Yeah, so if I take a cut there, if I take a strip, this is what you see. This is your slab with the UDL. Okay, the slab is loaded with the UDL, which could be self-weight or whatever. And do you agree with me that these are the direction of the moments? Yeah, same as we did before with the plastic theory. It's exactly the same. Okay, so we have got moments here. Now, along the yield line. Now, these moments here, they are moments along the entire length of the yield line. Yeah, okay, so we have moments along the length, which is what I have shown here in two dimensions. You see the direction. So we have a moment for the left side of the slab. We have a moment going this way, anti-clockwise, and on the right, for the right side, we have a moment anti-clockwise m. Okay, and they are obviously in equilibrium. Now, for the moment vector, read here, we use the right-hand screw rule. Okay, so using your hand, look at the left side here. Look at this left side slab. Now, using your right hand, using your palm, make the moment with your palm. This here, okay? So you make a palm. So we have an anti-clockwise movement, isn't it? So using your palm, you make an anti-clockwise movement. The thumb will give you the vector. Is that clear? So use your right hand. The palm here will give you, these fingers will give you the direction of the moment. So whether it's clockwise or anti-clockwise, and the thumb will give you the vector. So this moment here, this moment is represented now by this vector m. Is that clear? Using the right hand screw rule. Is that clear or not? Yeah. Okay, so you do the same now for the right side. So what do? This is your hand. Can you see that? Yeah. Okay, so you make with your thumb, with your palm, sorry, with the fingers of your palm, you make a direction of moment anti-clockwise, always with the right hand. Okay, you make that direction anti-clockwise, and the thumb will give you the moment. Is that clear? What you notice, very, very important, along a given yield line, the two vectors must be equal and opposite. They must be opposite direction because they are in equilibrium. Is that clear? So you can't go wrong. All right? Is that clear? Any questions? Okay, so that's for the moment. That's for moment. Now,
hello, sir. Can you describe how to get the direction of the moment again?
Oh, I wish you were here in the class, because if you're in the classroom, you can see me with my hands. Okay, I don't know if I can get the.
I can see you now.
You can see me?
Yes.
Okay, look at the left side, this part of the slab, okay? Use your hand, right hand, the right hand, okay? The fingers here of your palm, you use them for the moment. So you have a moment going anti-clockwise like this, yes, okay? So you make an anti-clockwise movement, and then your thumb will give you the direction of the vector. Is that clear now?
Okay.
Yeah.
Okay, your thumb will give you the direction of what?
It gives you that's the vector moment. So your moment here, this moment here, is now described by this vector. So you converted the moment into a vector. Okay, I don't know if you did physics in your secondary school, where we used to have, where we used to convert electromagnetic field. Yes, do you remember it? Where you have an electrical wire and you have an electrical, and then you have a magnetic field created by the electricity. It's a very similar thing. We use some thumb rules to get the to convert your electromagnetic field into a vector. It's very similar. Yeah, where you convert electrical field and electromagnetic fields into vectors. Do you remember that? It's very similar. Yeah. So what we're doing here basically is expressing the moments here in vectors, because then I can work in 2D, because I have a vector now. Okay. Now let's look at now this part of the slab, the left part of the slab. Do you agree that this slab here, when failing, it's going to rotate about this edge, about this side? Do you agree? Yes? You agree? Yeah. So when this part here of the slab is rotating about this side. It's rotating in which direction? In which direction? Down or up? Down. Now you use your left hand, not right anymore. You use your left hand, make a rotation going down with the left hand, and your thumb will give you the vector rotation. Clear? So using the left, I repeat again, this is the left side of the slab. Using your left hand, you make with your palm, make a movement going down, the rotation going down, and the thumb will give you the direction of that rotation. So you have now a rotation vector going this way. Is that clear? And you do the same for the right side, always with the left, always with the left hand. So going down, look here, okay, and the thumb gives me this direction.
For this example, moment and rotation vectors are in the same direction.
In this particular case, you can see that these two here are in the same direction. But you have to be careful, because later on, when we do a slab which is supported on 4 edges, you have to be a little bit careful. Yeah, but the main thing is to remember right hand for moment vectors, left hand for rotation vectors. And you do it for each region of the slab. You do it for each region of the slab, okay? I mean, and this is what I've shown here on this diagram on the left and right, so which is what I have explained now. Is that clear?
About the rotation, no.
Left hand. Yeah. So left hand, if you do it for the left side, for this one here, it's going down. The slab is going down, rotating this way. Yeah, when it's failing, this is the axis of rotation. It's rotating about this edge, and it's going down like this. So your thumb gives you this. Okay?
The axis of rotation is opposite to the moment vector.
The moment vector, you use the right hand, and the rotation vector, you use the left hand. In this case, you can see that the moment vector and the rotation vector are in the same direction. Okay? But what you need to remember, you use the right hand for moment, left hand for rotation. Okay? We'll do more of this so you get a lot of practice. Okay? Is that clear? Okay. So this is for the slab. What we've done here. Now we are going to analyze the slab here. This is the slab. Okay, pay attention with me, please. This is the slab here, rectangular slab. Okay, it is simply supported on two edges. The length of the slab in this direction, in the X direction if you want, is L, okay, is L, and the length in this direction is alpha L. Alpha L is just a factor. It could be 0.5, 0.3, whatever. Is that okay? Yeah. Now, the yield line, in this case, the yield line is going to occur at midspan, which is where the maximum curvature is. Okay, so we have a maximum. We have these are the moments. You can see the vector. In green we have the direction of the moments. Okay, so which is what we have here. Okay, and then we have the vector of the moments. We have the vector of the moments there. Okay, in blue, using the right hand screw rule. And then what I've done here, I've shown the vectors, rotation vectors, okay, which are in this direction here. All right. What are the these rotations here? These arrows in these are representing the rotation. Okay, they are not moments. Okay, they are just rotations. Okay, now. So this is the slab. If I take a strip of the slab, we have a slab which is simply supported. It's like a beam, basically, simply supported. Remember that the UDL, what are the units of the UDL on the slab? Do you agree it's kilonewton per meter square? Because it's over the entire slab. So your UDL, the units for the uniformly distributed load is kilonewton per meter square, because it's over an area of the slab. Okay. What are the units of moment? Can you see the units of moment? The unit of moment is kilonewton meter, isn't it? But per unit length, because it's over the length of the yield line. So it's kilonewton per meter. So it's kilonewton meter per meter. Please remember that. Okay. So the units of moment is kilonewton meter per meter, and the units for the load is kilonewton per meter square, because the load is applied on the area of the slab. Okay. Now, the rest is same as what we did with the plastic theory before. Okay. You have displacement here. Do you agree that displacement is L over 2 theta? Agreed? Yeah, it's L over 2 theta, okay, because we have symmetry, so you have the same theta there, okay? And we have the direction of the moments there. So the internal work, what is the internal work? What is internal work? Normally in plastic theory, what do we do? MP theta. MP, so we are doing the same. Look here, please pay attention. M theta. Why did I multiply by alpha L? You see, M is the moment. It's the ultimate moment. Times alpha L, because the moment is applied along the alpha L length. Do you agree? Because your moment M is applied over this length, alpha L. Okay? So you have M alpha L times theta for this part. And then for the right hand side, for this part here, we have the same M alpha L theta, which gives 2m alpha L theta. 2m alpha L theta. Is that okay?
Hello, sir.
Yes.
You said it's simply supported. There's supposed not to be moment at the end now.
There is no moment at the end. It's simply supported.
Okay,
it's not fixed.
Okay,
you only have a moment here
at the center.
There is only a rotation here. There is no moment. Okay, the moment is at the yield line here in the middle. Okay, because it's simply supported, so there are no moments here. Okay, if it was fixed, you have moment, but you haven't got. It's not fixed. Okay. So for the external work, what do we have for the external work? What is the external work normally if you have a UDL? If you have a UDL, you load by the average displacement. We are doing exactly the same. Look, this is the load here. This is the load times the average displacement. The only difference is that we multiply the load here by the area. What's the area of the slab? L times alpha L. That's it. So it's that the DUDL times the area of the slab, which is L alpha L times delta over 2. And you substitute here delta is L over 2 theta. So we substitute delta here by L over 2 theta, which gives me L theta over 4. And then you simplify, okay, which gives you W times alpha times L cubed. I'm sorry. So so it's W alpha L cubed over 4 times theta, and then when you equate the external work with the internal work here, so now equating the external and the internal work, you can see that the theta will cancel. Same as with plastic theory, the theta will cancel, and we have M is WL square over 8. M is WS square over 8. Does this result answer surprise you? What's the maximum moment if you have a simply supported beam with the UDL? W square over 8. It's exactly the same. It's exactly the same whether you have a slab, simply supported slab, or whether you have got a simply supported beam. The result is exactly the same. The only difference are the units here of M and W. That is the only difference. Okay? If you have a beam, M is kilonewton meter. If you have a slab, it's kilonewton meter per meter. If you have a beam, W is kilonewton per meter. If you have a UDL, if you have a slab, it's kilonewton per meter square. But the equation itself is exactly the same. Is that clear? Yeah. So here there is no, you could have expected this answer because we are dealing with a strip of the slab like a beam here. Okay. As I said, the difference are the units. Any questions on this? Any questions? Okay. Let's look at now. Let's move on. Are you ready? The next slide. This is more interesting now because now what we have a slab. I'm going to explain this very, very, very slowly. So pay attention with me, please. So we have got now a two-way slab. In other words, we have a rectangular slab which is supported on 4 edges. Simply supported on 4 edges. Okay. Now we have a truly two-dimensional problem here. Okay. Now this is the yield line. As we said before, this is how the yield line for a rectangular slab supported on 4 edges. The yield lines will divide the slab into 4 regions. Do you agree? We have region A, B, C, and D. A and C are identical in terms of area and so on, because we have symmetry, and D and B are identical. So the first thing we are going to do, we are going to determine the vectors, the moment vectors, and the rotation vectors for each region. Okay, so look at each region. Let's start with region A. Please pay attention. Let us start with region A. Forget everything else. Just look at region A. Just look at region A. Let's start with the vector here. Do you agree that this slab, this region A, will rotate about this side here? Do you agree with that? About this edge? Yeah. So use your left hand for the rotation and check that this is the correct direction of the vector in blue. With the left hand, okay, for region A, left hand rotating about this axis here, this side. Okay, so this is your slab, and it's rotating about this edge here, going this way. Okay, and using your left hand, okay, so you concentrate on this region here. Okay, concentrate on this region, and it's rotating about this side. Use the right hand. So the right hand, it's going down like this, about this edge. So the thumb gives you a direction like this to the left. Clear, everyone? Yes? Okay? Yeah? Yes or not? Good. Now, let's look at now the moment. The moments will be at the yield lines. Yes? So we have 1, 2, 3 lines. Look at the first line here, this line here, this one here. The moment, remember the moment is a moment of resistance. So your moment along this yield line is going up, out of the paper, up, okay? So use your right hand, it gives you this, look. Okay, is that clear? Clear? Do you agree this is the direction of the moment vector? So using your right hand, your thumb, your palm, you make the direction of the moment, which is in this case coming up from below, okay? And the thumbs give you the direction of the moment, okay? So it's like this, okay? So basically,
So what's the importance of the moment vector?
The importance is here. When I project now, I'm coming to it in a minute, when I project, okay? Because what you do, you project on the x-axis. We have two axes. We have the x-axis here, and we have the horizontal, and we have the y-axis. Okay. Now, for this yield line, this one here, again, are you satisfied that this is the direction of the vector? Yes. Now, for this one here, are you satisfied this is the direction of the vector? Okay. Always with the right hand. Okay. If you do region C, you do exactly the same. Using the right hand, you find that this is the vector moment for this yield line. This is the vector for this yield line, and this is the vector direction for this yield line. What do you notice? Is that the two vectors here along the yield line are equal opposite. They are in equilibrium. Okay. If you do the same for B and D, you get these vectors here. And again, along each of the yield lines, you find that the two vectors are equal opposite. Equal opposite. Can you see here? Equal opposite, equal opposite, equal opposite. So what I'm telling you now, in the future, don't waste your time playing with your hands for each region. When you do one region, you can deduce the other regions by using the equilibrium. Simple as that. Is that clear? So when I do region A, I know once I've completed region A, I know that this vector is opposite to this one. I know this vector is opposite to this one, etc. The other thing, notice here, very important, can you see that these vectors here for region A, for example, can you see the moment vectors going like a flow in the same direction? Can you see that? In this case, going around in a clockwise manner. Can you see that? Yeah? And the same here, you can see that the vectors, the moment vectors here for region C are going like a flow in a clockwise manner. And the same for the MB. Okay? So once you've done one region, if you do one region A, for example, you don't have to do all the other regions, you can deduce them and save time. Clear? Okay. The other thing you notice, can you see that the direction of the rotation vector here follow the same general trend of the vectors for the moments. And you can see here the same. See, you got this following the same trend. See that? Going from left to right, going from up, from top to bottom, etc. So there is there are some features that you can use in the future to save time. Okay, so now I've got the vectors in red. I've got the moment vectors, and in blue here I've got all the rotation vectors, and therefore I'm going to yes. The other thing we need to do is the best thing is actually to draw a table, okay? And this is what the table, I'm going to use the table to give me the work, the internal work for each of the 4 regions. We have 4 regions. So what you do, you create a table. Let me explain this. You create a table. You have the moment vector in the x direction. You have the moment vector in the y direction. You have the length of the yield line in the x direction. You have the length of the yield line in the y direction, the rotation vector in the x direction, the rotation vector projected on the y direction, and then you do the work here. And let me explain it for region A. Pay attention, please. I'm going to for region A. Let's start with region A. Can you see region A? This one here. Now, for region A, can you see these vectors in red? These are the moment vectors. When I take all these vectors here and I project them onto the x-axis, first of all, is it going in a positive or is it negative direction? Huh? Negative. Okay, good. Now, when you project this vector, start with this one here. When you project this one on the x-axis, it's m, isn't it? These are given. In the x direction, we have m, and in the y direction is 0.4 m. So these are given to us. The moment of resistance in the x direction is given to us as m, and the moment for this slab, the moment of resistance in the y direction is 0.4 m, okay? So now I'm projecting on the x-axis. So when you project these vectors here on the x-axis, you get m. That's the maximum you can get. Clear? You get m, okay? These vectors here, what do you get when you project now on the y-axis? Do you agree that this vector on the y-axis is 0? This vector here on the y-axis is 0. Yes? Yeah. Do you agree that these 2 vectors, this one here and this one here, when you project on the y-axis, gives you 0 as well, because one is down, one is up. Can you see that? This vector, the projection on the y-axis is down, and this vector here, the projection on the y-axis is up, and because they are equal, so you have 0.
That's the sum of
Huh?
That's the sum of these 2 vectors.
You're projecting all the vectors on the x. You take the region. For each region, you take the moment vectors and you project them on the x-axis. Okay?
So there are 90.
Sorry?
There are 90.
Not 90. We have symmetry here. The slab is symmetrical. The yield line is symmetrical. So the slab is symmetrical. So these 2 vectors here are equal in magnitude. Okay? Yeah. So this one, when you project on the y-axis, you get 0.4 m down. Okay? And this vector here, this one, when you project it on the y-axis, it's up 0.4 m. So you have 0.4 m down and 0.4 m up gives you 0. Okay? Is that clear? Yes.
Hello, sir.
Wait a minute. I'm listening to this question. Sorry, what did you say?
The vertical yield line, the horizontal yield line, sorry, at the middle.
Yeah.
The origin of the graph. Since we are making this zero.
No, you are projecting onto X.
Onto X.
You project onto X.
Then those two,
These two here, these two on the y-axis will cancel each other. But on the y-axis, when you project them, they give you M. M is your maximum. In the x direction, M is your maximum. In the y direction, your direction, 0.4 M is your maximum moment. That's your moment of resistance. Okay? So when you project, anything you project on the x-axis is M. Anything you project on the y-axis is 0.4 M in this case. Is that clear? And if you have vectors going in different directions, they will cancel each other. If they're going in the same direction, obviously they add up. They add up to each other. Clear? Yeah?
Yes, sir.
Yes.
That's on panel A. The diagonal moment are going in the same direction. They're supposed to add up.
Which are going in the same direction? Which ones? This.
Yes?
Yeah, in the x direction, yes. They are going in the same direction in the x direction, but not in the y direction. In the y direction, they cancel each other, these two. Okay? So you have no component on the y-axis. This is what I'm saying. Okay? Because they are going in the opposite directions on the vertical axis. On the y-axis, I mean. Is that clear?
Okay.
Yeah? That's why we need the vectors, because now we're projecting on the x and the y-axis. Okay? You do the same, for the yield line, do you agree with me that this yield line here going for region A, can you see the yield line for region A? When you project it on the x-axis, what does it give you? The whole yield line projected on the x-axis, what does it give you? 1 plus 1 plus 2, which is 4. Do you agree? Yeah. Now, this yield line again, when you project it on the y-axis, what does it give you? This yield line, you project it on the y-axis. What does it give you? 1.5. You agree? Yes? Okay. So we're projecting the yield line on the x-axis is 4, on the y-axis is 1.5. Okay.
Sir, can you explain that again? Which yield line are you talking about?
The yield line for region A. Look at the mice from there to there to there. That's the yield line for region A. Okay.
Okay.
And you projected that the whole yield line. You project it on the x-axis. So when you project this yield line on the x-axis, it gives you 4 meters. Okay. And when you projected this yield line here on the y-axis, it gives you half of 3, 1.5 meters. Okay? Is that clear? Okay. Now, the rotation, we do the rotations here and we have to finish today, okay? So when you do the rotation, can you see we are still looking at region A, remember? Can you see the vector here, rotation? This vector here, projected on the x-axis, is negative. Yes? It's negative, do you agree? Yeah? What is the value? What is the rotation? What is the rotation along this edge? Can you see the diagram I've got here on the right, on the left here for region A? Can you see this diagram? Okay, look, this length is 1.5. This length is 1.5, okay? At this point here, where the maximum curvature is, we always assume that the displacement is a unity. Is always unity. Why? Because the delta will always cancel. So there is no point in putting delta because it always cancels in the equations. So from now on, we assume that the displacement is a unit, 1.
So
Okay?
for panel A, what's the direction of the moment?
Direction of the this is the direction of the moment for A. That's the moment vector. Okay?
That means it rotates upward at the center.
It comes here. It's coming upwards from below upwards, and then using your right hand, it gives you this direction. We have already explained this. Okay? You see, it's going like this, and this is your thumb. Okay? It's going like this, and this is your thumb, which gives you this direction. Okay? For the moment, for the rotation vector here, you use the left hand, as we said. Okay? Which gives you this direction here. Okay, so when you take the rotation vector, this one here, when you project it on the x-axis, it gives you a negative value, obviously, because it's opposite the direction. And the rotation, imagine this region A rotating about this edge, and the maximum displacement there is 1. You have to think in your head, you have to think in 2 dimensions. Okay, this is your slab, this is your region A, rotating about this edge here. The displacement in the middle is 1. Okay, this length is 1.5. Do you agree that this is the diagram that we have? Do you agree?
Where are we looking at?
We are looking at this region here across, like here. We have 1.5, okay, and the displacement in the middle here is 1. And this is the angle of rotation of region A. Okay? Yeah? So we have, remember the rotations are very, very small, so the sine and the theta are the same in radians, okay? So basically what you have theta equals to 1 over 1.5. 1 over 1.5. 1, which is the displacement here, out of plane, 1 over 1.5.
How did you get 1, sir?
1 is, we assume the displacement is 1, because you can assume it's delta. When you put it in the internal-external work, it will cancel anyway, as we always did before. Okay, so you might as well give it a unit value for the maximum displacement. Okay, is it clear or not?
Okay, we can assume that the displacement is 1.
The maximum displacement here is 1, yes. Sorry? No, look here, look. This is 1.5. Look, think about it in 2D in your head. This is 1.5, okay? The displacement is 1 out of plane, and the angle between the two, the angle that this region A rotates about this edge is theta. Is theta, okay? So look at me. This is the edge. This is the edge, all right? Look at this carefully. This is the edge. This is 1.5, okay? It's going to rotate by an angle theta from there, okay? So this is 1.5, this is 1.5, this is 1, and this is the angle theta. So what is the relationship? Yeah, basically you've got, so you've got this angle theta, all right? And this is 1, this is 1.5. So you have got theta, okay? You know the relationship. This distance is 1.5 times theta. This distance here, 1 is equal to 1.5 times theta. So theta is 1 over 1.5. Okay? Clear? Yeah. So we have 1 over 1.5 theta with a minus, obviously, because it's going in 2 directions. Now, the vector here projected on the y-axis obviously gives 0. When you project this vector on the y-axis, it gives you 0. So there is no vector on the y-axis. Now for the work, you multiply. Remember, it's m times the length of the yield line times theta, isn't it? So you multiply
Sir,
minus m.
can you explain that virtual work on the y-axis again?
Do I explain what? Sorry?
You said the virtual work on the y-axis.
This vector here. This vector on the y-axis is 0 because it's horizontal vector. Yeah? So it has no component on the y-axis. So you have 0 there. Okay?
About the sides. At the first, you said that the sides are rotated around. And we think that which one work, and I assume that the depth is 1. We are confused about the hypotenuse and the adjacent side. So in case region A and B, you assume that region A and B, the hypotenuse is 1.5.
Yes.
And then in region B and D, the hypotenuse is not given.
We're looking at A at the moment. We're not looking at A or B, D or B at all. We are looking only at A.
The hypotenuse is 1.5 now.
Yes, this is 1.5.
So because it's rotated down.
Yeah, so one is down, one is no down.
Because it's the same length. That's one.
Yes, so it gives you this.
This is 1.
Yes, so you have theta is, you have 1.5 times theta is equal to 1. Okay? Now, now I think we are running out of time. So when you multiply mx times lx times theta x plus my times ly times theta y. And if you do that, you get 4m because you got m times 4 times 1 over 1.5. You can see that the minus and the minus here becomes a plus. So it gives you 4m over 1.5. Okay? It gives you 4m over 1.5. And this is only for region A. We haven't finished. Okay? So next week I'm going to come back to this example here. Okay? And explain it again and then finish it. Is that okay? Okay? So I'm going to stop the recording. Okay? And next week we will revisit this example. Okay? We are going to revisit again. So go over it on your own, please. Try to understand the vectors for the moments and the rotations. And then next week, as I said, we will have another look at this same example again. Okay, thank you.